Hi, welcome to another video. This video is to give you the solution to more homework problems. So let's start with homework 1. Okay, so for homework 1, let's do some additional solutions. And so for number 1 in homework 1, let's go over part D. Okay, so number 1, part D, this is for section 1.3.3. Okay, 1.3.3, number 1, part D. So it says define a sample space S for each experiment. So for part D, the experiment is toss a coin 3 times and record the outcome after each toss. This is very simple. The sample space is just heads, 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 tails, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, tails, tails, tails. H is for heads, T is for tails. Right, it's much easier writing H and T for heads and tails respectively than heads and tails every time, right? Okay, so then this is the sample space for flipping a coin 3 times and recording the result head or tails each time. Okay, so that's part D. All right. Also, a question the student had for me is part E. So the experiment is toss a coin until a head appears and record the number of tosses required. Okay? And so the solution for that is the sample space is just the set 1, 2, 3, 4, 5, 6, and so forth, dot, dot, dot. Right? These are the number of times it takes to get a head the first time. Right? It's the number of tosses required to get a heads the first time. And so the options you have is that you can get a head the first time. You can get heads, the first time you get heads could be in the second toss, the first time you get heads could be the third toss, the fourth toss, the fifth toss, the sixth toss, and so forth. And so that set S, the set of all positive integers, that's the sample space for experiment E. Okay? So that's part D and E of number 1 of that question. So let's move on to another question. Let's look at number 4. Okay, so for number 4, it says use Venn diagrams to verify the following statements. So for part B of number 4, same section 1.3.3, you want to verify that A intersection B union A intersection C is equal to A intersection B union C. Okay, so you want to verify this using Venn diagrams. So you want to show us the Venn diagram for this is the same as the Venn diagram for that. Okay, so if you look at A intersection B, right, we have 3 sets here. You have set A, set B, and set C. The 3 of them are represented by those 3 circles. A and B would be this part of the Venn diagram, right? And if you look at A intersection C, that's the universal set there, universal set there. So if you have a set A, you have a set B, and you have a set C again. Now A intersection C would be where A and C intersect. That would be that part. And so if you take this shade region and you union it with that shade region, the union of those 2 sets is then this set. So you have set A, you have set B, and you have set C. And so the union is you take that part from that Venn diagram and you union it with this part. And so that's the Venn diagram for A intersection B union A intersection C. And then here, if you have A, you have B, and you have C. And here you have A, you have B, and you have C. Okay? Then if you do B union C, then B union C is this. right? It's just what's in circles B or circles C. And if you do A, right, that's A here, right? But now we're going to intersect those two sets. So what's in both sets? And so what's in both sets, that's the universal set. And so for what's in both sets, you have set A, you have set B, and you have set C. And what's in both sets is what's in A, in circle A, and in one of those circles. And so what you get is here, here, and here. That's the only shaded part that's both here and here and there. Right? This part is only shaded here and not there. This part is shaded here but not here. This part is shaded here but not there. This part is shaded here but not there. But these three parts are shaded in both of them. So that's why it's in that Venn diagram. And so that means that this Venn diagram is the same as that Venn diagram. And so since these two Venn diagrams are the same, and this Venn diagram represents this set, and this Venn diagram represents that set, we're using Venn diagrams to show that those two sets are equal, to illustrate it. Okay, so that's for B. All right? All right, so, okay, so that's a quick review of some other stuff in homework 1. Let's go to homework 2. Okay, so for homework 2, if we look at, so this is homework 2. So for homework 2, if you have so for section 1.4.5, okay, so for section 1.4.5, let's say, let's quickly look at number 1 again in 1.4.5 homework 2. And it says A and B are mutually exclusive. So A and B are mutually exclusive. Okay, so A and B are mutually exclusive, and the problem gives you, right, P of A is 0.35, P of B is 0.15. Okay, so for part B, it says find the probability of A prime, right? So the probability of A prime is just 1 minus the probability of A. That's 1 minus 0.35. And so let me just, in the other video, I wrote 0.15 here. 1 minus 0.35 is 0.65, okay? So for part B, that's 0.65, all right? For part C, which we're going over now, probability of A intersection B, right? So the probability of A intersection B, what is that equal to? Well, first off, the probability of A union B is equal to the probability of A plus the probability of B minus the probability of AB, right? But okay, sorry, actually, I now realize this is just 0. Sorry, that's just 0 because A and B are mutually exclusive. Right? A and B are mutually exclusive. That means they can't happen at the same time. They're just joint sets. And so the probability of the intersection of those sets is the probability of the empty set, which is 0. Okay? So A intersection B being mutually exclusive, that implies that A intersection B is the empty set. That implies the probability of A intersection B is the probability of the empty set. The probability of the empty set is 0. Okay? Okay. So that's why that's 0 in part C. Okay? Okay, so that's number 1 in that section. Let's keep going. Okay, for number 4, 1.4.5, number 4, a card is drawn at random from a standard deck of 52 playing cards, so each card has equal probability of being drawn. Find the probability of drawing the following. So for part E, it says a card is neither red nor queen. Okay, so the probability of so R, I'm going to say is the event of drawing a red card, and Q I'm going to represent as the event of drawing a queen in the standard 52 card deck. Okay, and so what we want is the probability that a card is neither red nor queen. So it's R prime, Q prime. That means that the probability of the intersection of the set of cards that's not red intersected with the set of cards that are not red intersected with the set of cards that are not queens. So we want to find the probability of R prime, Q prime. Okay, so the probability of R prime, U prime, right, by De Morgan's law. Remember, De Morgan's law. Yeah, there's more than one way to do this problem. If you take R prime intersected with Q prime, that's the same as R union Q prime. Okay, so the probability of R prime Q prime is 1 minus the probability that is of R union Q. Okay, these two sets are complements of each other. And so the probability of R prime Q prime is 1 minus the probability of R union Q. So this is equal to 1 minus the probability that a card is red or queen. Okay. Well, in the deck, right, there's 26 red, there's 26 black. Okay. But among those 26 red, there are 2 queens and 2 queens that are red, and there's 2 queens that are black. Okay. So if you want the probability of red or queen, this is 1 minus the number of red or queens over the total number of cards in the deck. And so what that's equal to is 1 minus the number that are red or queen. There's 26 red, that includes 2 queens, and then there's 2 other queens that are not red. So there's 28 cards in total that are red or queen, divided by the 52 cards in the deck. So the number of red or queen cards is 28 divided by 52, which is the total number of cards in the deck. So 1 minus 20 over 52, that's equal to 24 over 52. Okay? And so if you simplify this, you get 12 over 26, you get 6 over 13, all right? And so you get 6 over 13. Yeah, that's the answer as a fraction. A little over 42%. Okay. So that's for E. Okay, let's do another one like this. Okay, so for 4E, for F, it's find the probability a card is neither a spade nor a king. So I'm going to say S is going to represent a spade. The card is spade. K is going to represent the card as a king. Okay, S is for spade, K is for king. And so you want the probability of the card is neither a spade, S prime, K prime. That's the intersection of the set of cards that are not spade with the set of cards that are not king. So I want to find the probability of S prime, K prime. And so that's equal to 1 minus the probability of S union K, just like the last example, but we're using De Morgan's law. And so this is 1 minus the number of cards that are spade or king, divided by the total number of cards in the deck. This is 1 minus that number over 52, the total number of cards in the deck. So for spades, right, so there's 13 spades, right? There's 13 spades, there's 13 clubs, there's 13 hearts, there's 13 diamonds. There's 13 of each suit, right? You need to know how the cards work in a deck. So it's 13 spades, right? One of those kings, there's a 1 king that's a spade. There's 1 king that's a club. There's 1 king that's a heart. And there's 1 king that's a diamond. Okay? So we want to know the number of cards that are either spade or king. We do not want to count a card twice, right? Or more than any number more than once. We only want to count each card exactly one time. So we have 13 spades. That makes up this one king. It's already there. So we have spade or king. We have one king that's a club that's not a spade. We have one king that's a heart that's not a spade. And we have one king that's a diamond that's not a spade. And so if you add these up, you have 13 plus 1 plus 1. There's 16 cards in the deck that are a spade or a king. And so that's a total of 16. So you get 1 minus 13 over 52. And so continuing that over here, that's equal to 52 over 52 minus 13 over 52, right? And that's 39 over 52. That's 3/4. Oh wait, sorry, 16 over 52. Right, 13 plus 30 is 16. So 52 minus 16 over 52, and that's 36. Okay, so it's 36 over 52, 18 over 26, 9 over 13. So the probability of that is 9 over 13. All right, so that's for F. So let's go to another problem. Okay, so let's keep moving forward. So let's look at homework number 3. So for homework 3, okay, so for homework number 3, let's look at 2.3.1, number 3, part A. Okay, let's look at that problem. So for that problem, it says a certain record collection consists of 10 records of chamber music. So there's 10 chamber music records. There are 15 vocal music records. And there are 20 symphonic music records. Okay, so we have those amounts for each one. Okay, there's a total of 45 there. Okay, so we have 10 chamber music records, 15 vocal music records, 20 symphonic music records. Okay, so we'll find the number of ways 2 records may be selected from each of the 3 groups of records. Okay, so I want to choose 2 of the 10 chamber music records. I want to choose 2 of the 15 vocal music records and 2 of the 20 symphonic music records. And so that amount is just 10C2 times 15C2 times 20C2. Okay, that's the number of ways to choose 2 of each group. Okay, and so if you calculate this, what is 10C2? It's 10 times 9 over 2 times 1. What's 15C2? It's 15 times 14 over 2 times 1. And what's 20C2? It's 20 times 19 over 2 times 1. Right? And so when you calculate that, you get the answer. 10 times 9 over 2, that's 45. Okay, 90 divided by 2 is 45. 14 over 2 is 7. 7 times 15 is 105. So 45 times 105 times 20 over 2 is 10. 10 times 19 is 190. So it's 45 times 105 times 190. Okay, so let's do 105 times 45. So 105 times 45, so you get 4,725. Okay. Good, that's right. So now this times this is 4,725 and then multiply by 190. Good, 45. Okay, so you get 1,167,750. And you multiply 4,725 by 190. Okay, 100. Good. Okay. So then, okay. So you multiply those three numbers, and you get 1,167,750. Okay. Okay. So that's the answer to 3A. Okay, so that's another problem to study. Okay. Okay, so let's do one in homework 4. Okay, so for homework 4, let's look at 3.3.2, number 4. Okay, so for this problem, A and B are independent. A and B are independent. P of A is 0.5. P of B is 0.8. Find the probability that neither events A or B occurs. So find the probability of A prime, B prime. Okay? So we'll find the probability of A prime, B prime. All right, well, the probability of A union B is equal to the probability of A plus probability of B minus the probability of AB. But wait, okay, so first A and B are independent. That implies that the probability of AB is equal to the probability of A times the probability of B. That's equal to 0.5 times the probability of B, which is 0.8, and that's 0.4. So the probability of AB is 0.4. Okay? So the probability of A union B being that is the probability of A, which is 0.5, plus the probability of B, which is 0.8, minus the probability of AB, which is 0.4. Okay? And so if you add those up, you get 1.3 minus 0.4, which is 0.9. So you get the probability of A union B is 0.9. Okay? So far we have that the probability of A union B is 0.9. Now the probability of A prime, B prime is 1 minus the probability of A union B. And why is that, right? Because again, A prime, B prime is the complement of A union B. By De Morgan's law, the complement of A union B is A prime, B prime. Right? The complement of A union B is A prime, B prime. So the probability of A prime, B prime is 1 minus the probability of A union B. Okay, so we found the probability of A union B, it's 0.9. So 1 minus 0.9 is 0.1. And so probability of A prime, B prime is 0.1. And so we found the probability of A prime, B prime, it's 0.1. All right, and so that's the answer to, in homework number 4, 3.3.2, number 4. All right, so I hope this helped a little bit more. Everybody had other answers, and these are more of them. Okay?